All right, so this is chapter 5, questions 12, 13, and 14. Actually, uh, question 12 is a little bit of a throwback to stoichiometry and all this fun stuff that we did at the beginning of the semester. So let me show you why. In question A, they're asking us how much heat is released when 85.9 moles of propane reacts. Right away, we see the moles. So we're like, dang, we got to go back to moles. Well, that's going to actually help us a little bit because it's going to be really easy. So basically, when you get something like this, just remember when you get 1 mole of propane, C3H8, that just means that 1 mole is going to give you negative 2,220 kilojoules. Same goes for 5 moles of O2. So when you react 5 moles of O2, you're going to get negative 2,220 kilojoules. Blah, 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 blah. Same goes for the rest. So if they give us 85.9 moles, this is where we go into A. If they give us 85.9 moles of C3H8, right? H8, I think. Yeah, okay. Everything's balanced. Then that means that we can use that ratio of negative 2,220 kilojoules per 1 mole to solve how much heat we would release if we had 85.9 moles. So this would be negative 2,220 kilojoules on top, because that's what we want to end up with. We want to end up with energy, the heat, for 1 mole, because that's what the chemical equation gives us, C3H8. So we just multiply 85.9 times negative 2,220, and we should get something like negative 190,698 kilojoules. All right, so that's an easy one. But how would they make it a little bit more complicated? Well, they would just give us grams to start with, just like they did in part B. Now, this is easy for us because we can easily go from grams to moles and from moles to kilojoules. So for example, part B, we start off with either 20 grams of propane and 20 grams of oxygen. Now, remember back when we were looking at stoichiometry, one of the things we had to look at was limiting reactants. So for this one, before we start calculating kilojoules and all that, I want to find first the limiting reactant. So we can do that with a molar ratio. So that means that I got to go from grams of propane and oxygen to moles of propane and oxygen. We can do moles of propane first. We get 20 grams of propane times the molar mass of propane, which is 44.097. 44.097. Just fix that mistake real quick. There we go. 44.097. Okay. Now we would divide that 20 over 44.097. 097. We get 0.4535 moles. Okay, so 0.4535 mole of C3H8. All right, 20 grams of oxygen, 20 grams O2 for 1 times 1 mole O2, and then we got, well, O2 is gonna be 32. 32 grams. Okay, or 31.998, whatever you want to use. I'll use the simple one. Let's do 32 grams. So 20 grams divided by 32 grams equals to 0.625. 0. Get out of here, man. 625. We do a little ratio. Of what it's supposed to be. So here, using this right here, oxygen and propane, we're supposed to have 5 mole of oxygen for every 1 mole of propane. C3H8. That's a 3. Don't worry too much about that. But if we look here and we put in our calculator, 0.625 divided by 0.45 is going to give us something lower than that. So we should have a 5. We should have a ratio of 5. But again, 0.625 over 0.4535. We'll see if we can get that to work. Yes. It's 1.38. So it's not 5. There's limiting reactant here is oxygen. Okay? Because there's less oxygen than there's supposed to be. If we had enough oxygen, it would be a number closer to 5. So here we are only going to worry about oxygen. So if we get rid of all this, actually, I don't know if I should get rid of that. I'll keep it on there. But we'll do this. We'll do it over here. So now that we figured out that oxygen's the only one we got to worry about, we can use the moles. Okay, 0.625 mole of oxygen times the ratio of moles and the kilojoules. So we got 5 moles of oxygen for every negative 2,220 kilojoules. So we got to multiply this times negative 2,220 kilojoules over 5 mole of oxygen. And we'll get, let me work this out real quick, 0.625 times negative 2,220. That should give you negative 1,387.5. And then don't forget, you got to divide that by the 5 moles. Because we don't exactly have 5 moles, we only have 0.625. And there we go. We get negative 277.5 kilojoules. There we go. Don't forget your kilojoules. All right. Whoa, kind of went crazy on there. Oh my God, that's just the first question. A piece of copper. Whoa. A piece of copper of mass 20 grams at 100 degrees Celsius is placed in a vessel of negligible heat capacity. Oh, whoa. Okay. But containing 50.7 grams of water at 22.2 degrees Celsius. Calculate the final temperature of the water. Assume that there is no energy loss to the surroundings. So here we're dealing with specific heat. That means we're going to use a slightly different formula, which is Q equals MC delta T, or MCAT. Apparently some people call it MCAT, where M is mass, C is, get out of here, man. Okay, C is the heat capacity, and delta T is the change in temperature. Now, here they gave us copper and water. In this system, we are having to mix the copper and the water, which means that their heat gained and their heat lost is gonna be the same, right? Because the copper is really, really hot. The water is normal temperature. So when the metal cools, the water is gonna absorb that temperature change. So we can do the Q, or the heat of the specific heat of copper. So copper is going to be red. M times 0.38, let's do that, times the delta T is going to be equal to the mass of water, however much water we have, times the specific heat of water, 4.18, times the temperature change of water. Okay, so all we really got to do is plug in our numbers. It's going to look a little funky when we kind of put everything together. Let's just use black. But you guys know left is copper, right is our water. So mass of copper is going to be 20 grams. That's fine, we can keep it like that. 20 times 0.38. Now remember, our change in temperature for our water, right? Sorry, for our copper. We are starting at 100 degrees Celsius. So if we go 100 minus T, okay, and T is our final temperature, right? Then we can go equals the mass of the water, which is 50.7. Okay. Times 4.18. And then the change in temperature. Well, actually, this was going to be the opposite of our change in temperature for copper. Because remember, the copper is losing heat. The water is gaining heat. So T minus 22. Okay. So now we just got to multiply these little things out. 20 times 0.38. Okay. That gives us 7.6. 100 minus T. But then we can do a little thing like that, little distribution. This one is going to be 50.7 times 4.18. Okay, there we go. That's going to be equal to 211.926 T minus 22. And now remember, we can also do a little distribution here. Okay, so that means that for 7.6 times 100, we got 760 minus 7.6T equals 211.926. T times, well, minus, but I gotta figure out how much this is. 22 times 211.926. And we got minus 4,662.372. I remember these numbers just came from distributing the multiplication of these numbers. Distribute it like that, like so. And then you end up with this. Now, what can I do with these? Right away, I can go from this t to coming to this side, and this number switching over to this side. All right. So if I want to do that, that means I gotta add 760 plus 4,662.372, and we get 5,422.372 equal to 211.926. No, plus, 211.926 T plus 7.6. Then we have to divide. Basically, we're just solving for T at that point. Okay, so 211.926 plus 7.6, that's going to give us 219.526 T. And then we just divide, like I said, 219.52 over 219.52, and we'll solve for T that way. So this divided by this, and we get 24.7. 24.7, that's going to be our T, our temperature, okay? The final temperature of the water, okay? So it went from 22 degrees Celsius to 24.7 degrees Celsius. Not too bad. Okay, over here, calculate the heat that must be supplied to a 500-gram stainless steel vessel containing 450 grams of water to raise its temperature from 25 degrees Celsius to the boiling point of water. Boiling point of water is 100 degrees Celsius. What percentage of the heat is used to raise the temperature of the water? So two-part question right here. In this question, interesting. Okay, sorry. Oh, got distracted. Calculating the heat. This one's a little bit different from number 13 because in this one, there's not really a transfer of heat between these two things. But it means that to heat the water, part of that heat is going to be absorbed into the stainless steel. So not only do I have to add more heat because part of the heat that is applied is going to go into the stainless steel, this just means that I have to add the heat that it requires to raise the temperature of stainless steel and the heat required to raise the temperature of the water as well. So we're doing it double, and then we're going to add that together. So we can start with steel, because we get that one right away. So 500 grams of steel. Q equals mc delta T. They give us specific heat of stainless steel. Mass of stainless steel is 500 grams times 0.51. And then remember, the temperature that we're trying to get to is 100 degrees Celsius. So the difference from 100 to 25 is 75 degrees Celsius. So we just multiply all that out. So 500 times 0.51 times 75. Okay, and we got 19,125. All right, then we got to calculate this. We'll do steel, and then we got to calculate the heat for water. Okay, so water is going to be 4.18. The mass of water, oh, different mass of water. We got 450 grams of water. Specific heat is 4.18. And then the temperature change is going to be the same, 75 degrees Celsius. So same as last time, 450 times 4.18. So, okay, times 75 is going to be 141,075. So 141,075. Remember, we're adding these two because we have to raise the temperature of both the water and the stainless steel. So 141.075 plus 191.25, sorry, 19,125. That's going to come out to 160,200. So that's how much heat we need to raise the temperature of stainless steel and water. Now, second part says what percentage of the heat is used to raise the temperature of the water. So we take this number right here, 141, and then we do a little fraction, 141,075 over the total heat that is required, which is 160,200. We're going to do that times 100 because that's how we get percentages. Get out of here, man. Log, I think. Okay, so 141,075 divided by 160,200 times 100 equals 88.062. We'll just leave it at 88 just to be safe. We'll be good to go. All right. Perfect.